Hi and welcome to the IEEE-NITK Virtual Expo. Today I will be talking about one of the year-long projects, Adversarial Attacks and Defenses in Reinforcement Learning, which was done under the CompSoc SIG. So my name is Videy, and other members who were the part of this project were Madhupanna, Akash and Saurabh, who were from the third year, and Kinshuk and Manav from second year along with me. We were mentored by Moksha, who is in final year. So let's get started. To give a brief introduction, reinforcement learning or RL is a type of machine learning where the learning happens through rewards and punishments, involving a feedback loop between the agent and the environment, bounded and formalized by a mathematical framework. The objective of the agent is to learn a function that exhibits desired behavior in the environment. Let me break this into simple terms. We have an agent or n agents that receive a set of observations from the environment. They take certain actions which are fed back into the environment, and the environment returns a set of next observations and rewards or the feedback. And this loop continues. So this is RL in its most simplest and naive format. This can get complicated in various ways when building real world systems, like when using function approximators or multiple agents, adversaries, or maybe a poor model of the world, having scalability and stability issues, etc. In this project, we aim to explore one such direction. So, talking about deep reinforcement learning, we basically use the representational capacity of the deep learning models like deep neural networks to learn the functions, or to be a bit more formal, I should say the policies and the value functions. A policy is just a function mapping from states or observation to actions or a distribution over actions. It formalizes the notion of behavior. Value function is basically the average expected return by following a certain trajectory. In the past few years, there have been great developments in this framework of reinforcement learning when combined with deep learning techniques, supplemented by enormous compute power that has become available. And deep RL works, and it works with so-called superhuman level performance on certain tasks. So whether it may be playing the game of Go, chess, Dota or Atari games, or online advertising, applications in medicine for protein folding, robotics, etc., Deep RL has found numerous amazing applications. I have highlighted a few of them here. This is a work from Min et al. 2015, playing Atari with deep reinforcement learning, where they proposed the popular deep Q network algorithm, and they were able to achieve better performance on the human benchmark on many of the Atari games. This work is a bit old, 2015, and there have been more advancements in this area. A few months ago, Google DeepMind released a system called Agent 57, which was able to achieve superhuman level performance on all of the 57 Atari games. Next is this work from Bansal et al. 2018, Emergent Complexity via Multi-Agent Competition. Here they train reinforcement learning policies via self-play in multi-agent environments which closely resemble the real-world settings. And they are able to achieve very good results in terms of learning complex behaviors like running, pushing, ducking, dodging, fooling the opponent, etc. And along with the transferability of the policies in the other environments. Now moving on to some robotics works. This is a work from the robotic manipulation domain by Kalashnikov et al. 2018. QT-opt scalable deep reinforcement learning for vision-based robotic manipulation, where they train robotic arms to manipulate real-world complex objects. And it works quite well. In fact, this is one of the state-of-the-art systems that you can build for this task. And there are many more such applications. The list goes on. But sadly, it's not enough. Let me motivate this with an example from supervised learning. So this is an example from Goodfellow et al. 2015, explaining and harnessing adversarial examples. On the left, we see an image of panda, which is classified with 57.7% confidence by a standard and one of the state-of-the-art deep neural networks. There is some procedure carried out in between, and we get a new image, which closely resembles the original one. In fact, on this slide, there seems no difference between the left and the right image. Despite this, the right image is classified as a given by the same deep neural network with about 99.3% confidence. But how is this possible? So this is a simple illustration of one of the adversarial attacks and is carried out in the middle. This image, which looks like some random noise or a random permutation of pixels, is a carefully computed permutation in order to fool the network. It is multiplied by some constant factor and added to the original image. The resulting image is an adversarial example corresponding to this example, on which the model makes a mistake, despite being trained with rigorous methods initially to classify images. An important point here is that what we just saw is not the property of this particular image, and neither it is a characteristic of deep learning or neural networks. This attack is fundamental even to the simplest linear machine learning models that we see, and because neural network architecture built on these models, they inherit this flaw. Okay, so now being a bit more formal, adversarial examples are the inputs to machine learning models that an attacker has intentionally designed to cause the model to make mistake. This definition seems to be very simple, but it has a deep interpretation when we will discuss the attacks further. And and as you might expect, such attacks exist in reinforcement learning settings too. And the objective of this project was to explore such adversarial attacks in single as well as multi-agent domains. Broadly, we discuss two scenarios. First is the pixel-based attacks. So this attack method is inspired directly from the way the adversarial examples are generated in the supervised settings. So exactly same as this one. We attack deep RL systems that take image pixels as the state or the observation input using the Atari 2600 games as a benchmark in white box as well as black box settings. So informally, what white box means is that the adversary has complete information about the agent, and black box means that the information available is limited. The second is the adversarial policy. So this type of attack closely resembles the way an attack would be carried out in real world situations. So here we train an adversarial policy in competitive zero-sum continuous control and robotic environment created from the Mujoko simulator. The attack is accomplished via training an adversarial policy with black box access to the environment. And as we will see, both of these methods fail the state-of-the-art systems in their respective domains. So now talking about the pixel-based attacks, here we assume that the adversary is inside the agent environment loop. So recall the agent environment loop that we saw initially. Here we assume that the adversary can manipulate the observation that is fed to the agent or the victim from the environment. Also, the adversary need not have complete information about the agent itself. So as I told, the attacks are also possible in black box scenarios. Okay, so first let us see some pre-attack videos. Here is an agent which is trained to play Pong. So the Pong is basically a table tennis type game where the goal is to score more points by manipulating the position of the pedal. If the other player misses the ball, then you get a point. Okay, so here is a random policy where the function approximator or the neural network is initialized with random parameters, and as we can see, our agent at each step it takes random actions, and it is not able to play very well. So that's because it's not trained right now to play. Now let us see the second one. So this shows a policy trained for about 20 million time steps via proximal policy optimization, and we see that our agent becomes an expert at playing the game, and it beats the opponent most of the times, and it is even able to beat the best human player. So yeah, as we can see, the reward goes to 21. Okay, now coming to the adversarial attack. On the left is the input frame to the network, and this is just a 210 cross 160 cross 3 matrix with each entry in the matrix representing the pixel intensity. If there was no attack and this was the input to our RL agent, then the action taken would have been up. And as we can see, going up is the optimal thing to do here. Like the ball goes here, and going up would be the optimal thing. However, because of the existence of the adversary in the loop, it perturbs the original input by a small amount. And here it is a permutation of the pixels computed, and this is multiplied by some small perturbation factor epsilon. In this case, the value of epsilon is 0.02, which is 0.002, which is extremely small. The output perturbed frame looks exactly the same as the original, but believe me, these two images are different. One cannot figure out a difference between two. At least the human eye cannot. And as we see, the action taken by our RL agent changes to down due to this attack, which, as you might expect, could cause the agent to lose the point in this situation. Okay, so now showing some results. The plot on the left shows a curve where on the y-axis we have the average return per episode of our RL agent, and on the x-axis is the increasing value of epsilon, which controls the amount of perturbation. We see that the return is close to 21 when there is no perturbation. So one game of Pong is of 21 points, so that's why it shows 21. Then as we see that as we increase the perturbation, the average return decreases exponentially, becoming close to minus 18 when epsilon is equal to 0.001 and close to minus 21 after 0.002. So this means that our agent loses almost all the time. On the right, the upper 4 frames are the non-perturbed input, where the lower ones are the perturbed ones with the highest perturbation 0.008 that we tried. There is a little distortion that you can see visible in the lower range of images, but it's not as if these images became blurry or completely unrecognizable. And our attack is 100% successful, and we need not even do this with such large perturbation. As we can see from this graph, a perturbation of even 0.002 is sufficient to bring the attack to a success rate close to 100%. Now let us see this happening. So this is the same trained policy as the previous, which was playing the Pong as an expert and beating humans, and this video illustrates the attack with a perturbation of 0.002. Okay, so first thing to note here is that the frames are exactly the same. They are indistinguishable from the original ones, and the RL agent performs very badly. As we can see, it takes wrong action most of the times and is losing every point. And yeah, I should highlight the fact that there have been no changes made in the two agents on the left and the right. They are the same as the previous, just we have carried out the attack procedure, and our RL agent loses most of the times. Okay, so we discussed the pixel based attacks, and those perform quite well, but the constraint that the adversary has to be a part of the loop can be unrealistic in certain cases. Hence we have a more realistic multi-agent threat model where the adversary influences the other agent or the victim by taking certain adversarial actions, which in turn affect the victim's observations. So the victim as same as our RL agent. So this is different from the pixel attacks where the adversary could perturb the input directly, and this is seen commonly in various applications. Let me take an example of say self-driving cars. In such cases, the adversary cannot directly manipulate the pixels from the camera or the car. Or it cannot do things like make a building disappear, or it cannot make such drastic changes. Hence, this attack is applicable even in the real world settings. We make a simplification by making the victim agent part of the environment itself. So what this means is that we fix the victim agent's parameters, and by doing so, we essentially make it a part of environment. And doing this, we now have a single agent RL problem where our agent is the adversary. And this is not an unrealistic assumption. In common applications of reinforcement learning or machine learning in general, we train a system and then we freeze or seal it for deployment. Hence the attack can happen in certain situations. Okay, so now coming to the environments, we have 3 of them created using Mojoko. This is a football type environment where the objective of the kicker is to kick the ball into the goal post and the goalie defends it. Next is the environment called You Shall Not Pass, where the aim of the runner is to cross the finish line with a stable gait, and the blocker aims to stop it. And lastly, there is a sumo environment where the objective of both the agents is to knock the other one out. Note that all these environments closely resemble the situations that we encounter in real world. Okay, so first let us see the performance of the agents prior to the attack. Here the policies are trained via self-play for about 700 million time steps, and as we see, both the agents are quite skillful in their work. Yeah, so the runner tries to dodge the opponent and reach the finish line, and the blocker tries to push it to make it fall or to make it lose the balance. They might not always be doing the correct thing all the time, but still it works, and it behaves in quite a realistic manner. Next is the policies in the kick and defend environment. Okay, so here we see the kicker goes towards the ball and kicks it in different directions, aiming to avoid the goalie and hit the goal post. And the goalie follows the kicker and jumps in the direction of the ball to save it. These agents might not be ready to play the Football World Cup, but certainly they are not bad, and we can see that they have learned to play football up to a decent level. Yeah, so the most important thing here is the time taken to train these self-play policies, which is approximately 660 to about 700 million time steps. Okay, so how do we carry out the attack? Unlike the pixel attacks, here the adversary influences the victims through its actions. And as discussed, we embed the victim in the environment, treating it as a single agent system. Then we train an adversarial policy, an MLP or an LSTM policy with proximal policy optimization for about 20 million time steps. And note that this 20 million is less than 3% of the time steps that were used to train the other agents. And these adversarial agents receive a sparse positive reward at the end of the episode if they win, and negative if they lose or tie. Okay, so yeah, on the left it's the same video as we saw previously. Yeah, it's the same on the kick and defend environment. This is the normal goalie versus the normal kicker. And on the right we have the adversarial attack, where the goalie plays the role of the adversary. Okay, so something bizarre just happened. The kicker, instead of kicking the ball, goes towards the goal post and bumps into it, which is highly non-conventional when it comes to real-world football. The adversarial goalkeeper shows a seemingly random behavior by lying down on the ground. It makes no effort to save the ball. Instead, it folds its limbs and lies down in a painful-looking contorted position. Yet we see that the adversarial goalie is able to beat the kicker. And it does this with a high win rate and in all the environments that we saw, in the sumo as well as in you shall not pass. Here is an illustration of the same adversarial policy against different victims, and this can be achieved by training victim policies with different random seeds. So this one shows the kicker going away from the ball and from the goal post. One would not expect this in an actual soccer game, that the goalkeeper is lying down and the player, instead of kicking the ball, it goes away from it. In this, the kicker moves very close to the ball, and instead of kicking it, it bumps into the goalpost again. And here we see another strange behavior of the kicker, where the kicker is moving towards the goalkeeper. And normally what we see is that the football player would like to stay away from the goalkeeper, but not when you have an adversarial attack. So all these illustrations suggest that the attack method is robust and not only beats one victim policy, but with many different seeds. So these are 3 different experiments with different random seeds. And also note that this is the same kicker as the previous one, which was playing soccer very well before the attack. Okay, so some important observations. First, this attack works successfully against many different victim policies. Highlighting this is important as the policies which we attacked are trained explicitly to be robust via self-play methods, standard self-play methods. The second is that the adversaries do not beat the victims by becoming stronger opponents, but instead with seemingly random behavior. And this again is similar to the pixel attacks, where the perturbation seems to be random, but it is carefully computed by the adversary. And note that this also forces us to go back to the way we defined adversarial examples. They are the inputs to the machine learning models, which an attacker has intentionally designed to cause the model to make a mistake. These inputs are direct in case of pixel based attacks, as we saw, and indirect in case of such competitive games where we need to train adversarial policies. The third is that the adversarial policy is not just out of distribution. Okay, so one might think of it as the victim policies as the adversarial policy just being out of distribution. but the victim policies are strong enough to beat out of distribution policies like a random or a lifeless policy. Also, the adversary wins by taking actions that are naturally adversarial to the victim. And this can be verified by plotting Gaussian mixture models and visualizing the activations via t-SNE visualization. Yeah, and another interesting observation is that clearly the victim and the normal opponent were not in Nash equilibrium. Because if they were in Nash equilibrium, then no adversary would be able to exploit the victim. So summing it up, the existence of such attacks is a setback to machine learning community, and also it is not very expensive to carry out these attacks. In fact, in all the attack methods that we saw, training an adversarial agent or generating adversarial inputs is much less compute intensive as compared to the training procedure of the RL agent itself. But despite all this, such analysis of such attacks helps us build more robust systems and be prepared for good worst case performance. As a part of this project, we also studied numerous defense mechanisms that have been proposed for this. And for those of you who want to explore more into why and how these adversarial attacks happen, and what are the vulnerabilities associated with the powerful deep learning models like neural nets, and what can we do to defend our systems, then feel free to check out this blog post on adversarial attacks and defenses in machine learning with a specific focus on reinforcement learning. And all the code for this project is available in this repository, and we also have a blog where we had posts on various topics that we learned during this project. Thank you.